So welcome everyone. We are going to have a presentation on sample and population distributions. Um, so let's basically start. In statistics, we look at samples. Okay, we collect data from samples, not the entire individuals in a given population. So basically, we make conclusions uh, on populations based on what we have got from samples, and that is what we call inference. Okay, so we make inferences on populations based on what we get in our studies, which usually rely on samples. So we need to understand concepts related to sample and population distributions in order for us to make accurate inferences about the entire populations. Now, um, when we talk about population distribution, we refer to how a particular variable is distributed in an entire population. This is to say that if we want to look at the height of individuals in monarchy, okay, monarchy is a place in Juba. So that means that we need to take measurements for us to get the population mean height, for example. In this case, the height is basically the variable, and we want to know the distribution of height in the entire population or for all the people who are staying in monarchy. We need to take these measurements, and then the distribution of that particular variable, which is height, becomes the population distribution for height for people who are staying in monarchy. Okay, now let's look at the concept of sample distribution. So instead of us taking measurements for everyone who is staying in monarchy, we choose a few people, or we select a few people who become our samples, and then we take their heights and then get the average height, and then we say that the average height in this particular study based on this sample for these people staying in monarchy is, let us say, 2 meters. Okay, so that becomes the statistic that we have got, sample statistic, and we are making a conclusion, or we are inferring that the population of monarchy, uh, they have a height or average height of 2 meters. Okay, so we usually base our conclusions from a sample. So in our sample, what is the distribution of the height? Okay, which is the variable in this case. The variable can be anything. It can be the height, it can be blood pressure, it can be anything that we can measure, or any characteristic that we have interest in. Okay, so still, it can be about height, can be about anything. Instead of looking at the 1,000 people staying in monarchy, we only choose 500 people, and then that becomes the sample distribution of height for people who are staying in monarchy. So what is the relationship? The relationship is basically that uh, the the distribution of a particular variable in a sample gives us a clue on what conclusions we can draw uh, about a particular population parameter that we are interested in. Okay, so that is what you need to know. Uh, for for us to make this conclusive or valid inferences, it means that we need to have sufficient sample sizes to be able to make conclusions about the population. So for whether you take measurements from the entire population, or whether you take measurements from a sample, the statistical measures that you use will basically be the same. If it is the height, you look at the mean height, then you look at the standard deviation, the range if you're interested, and things like that, and also skewness. You'll be interested in those things. So you can still apply the same statistical methods, whether it is a sample or population. But what you need to know is that the sample distribution may not be exactly like that of the population. This could be because of issues to do with sampling or sampling variability. So we need to look at the distribution patterns. How, if you did take these measurements, how will the data look like? If you enter them maybe in a graph, maybe in a histogram, created in histograms, what will the patterns be and what will they really tell us? So one pattern that will happen is that you will have data that is balanced. That means that let us say the left hand side is almost identical to the right hand side. So you get what we call a balanced shape. So that means that the side on the left of the mean and the side on the right of the mean will actually be equal. And basically these are what you call the normal distribution, which is very common, and then also what you call uniform distribution. But sometimes you can get curves that are not really symmetrical. Okay, so we call them being skewed. So we call that skewed distribution. Okay, so skewed distribution can happen. So we can have positively skewed and then also negative skewed. A positively skewed is when you have the tail, the long tail of the curve being towards the higher values on the horizontal axis. When we have the curve, the tail tending towards the lower values, then that is a negative skew. So that pattern is actually not symmetrical. We can have another pattern where you have two peaks, or you can say you have two modes. This indicates that you have two different groups, or you can have subgroups with a subgroup within a bigger population, or a larger population actually. So for example, you can have students forming what we call a bimodal distribution. You have those that are scoring highly, and then those that are scoring lower marks. Okay, so you have kinds of peaks in terms of their performance. Two peaks. Okay, so that is if you have the frequency and then the scores as your parameters that you're looking at. For uniform distribution, you can get this if you have each value of what you're likely to get having an equal chance of being observed. So for example, if you throw a dice, the dice will give you any of the 6 faces. So the chances of getting any of the faces 1 up to 6 are equal. So you get a uniform distribution. So that is an example of a dice that we hope you see. So we look at what we call a normal distribution. A normal distribution is when you have, it's actually what we had earlier on discussed, but I think we did not give more elaboration. But basically, a normal distribution is the symmetrical distribution, like we saw. It is bell-shaped, okay, and it has a specific mathematical pattern that it actually follows. So therefore, the peak is usually the mean. The peak is usually at the mean. And then you have a symmetrical decline from either side. On the right and the left, the decline is actually similar. So usually the mean, the mode, and the range, they are usually within, they're actually close, very, very close. Okay. So standard deviation, which is basically the distance from the mean. If you move one standard deviation from the mean on either side, you are covering about 68% of the population will lie within that. So an example, actually, let us come here. An example of a parameter that falls under normal distribution includes the height, weight, IQ, intelligence quotient. They tend to follow what we call normal distribution. This is to say that if you get a sample, you get people and plot their heights, you get a curve like this. Okay, how many people have 1.5? You plot the frequency against their height, so you get a curve that is like that. So most people, of course, will be around the mean and the mode, and then most of them would actually be here. Okay, so that's the same for height, for weight, for IQ. It's a normal distribution, and usually the mode, the median, and the mode, the median, and the mean are always around the peak. So if you move, I said if you move one standard deviation from either side, 60% of the people will be under that category, which is marked here. So from here to here, it is 60% of all individuals will fall under this category. But if you move two standard deviations from either side, you will have about 95.4%. It covers that total area. So most of the people will be there, about 95.4%. So what does this? Why are we really very interested in this? We are interested in this because it can enable us to make predictions even in the things that we do in our practice. So for example, you are a hospital manager. You're a hospital manager, and you want to purchase dressing material, but the dressing material come in different sizes. Assuming you're interested in dressing material that is for arms. So if you look at the average arm circumference of the population that you actually receive, then you can be able to make that decide to say, okay, if I'm purchasing, if for example I need dressings of let us say medium size will be able to cover a population of, let us say, if you most of them you buy medium, but you also have a few of a larger size and a few of a smaller size. When you do that, you actually incorporated into the concept of standard deviation. in making your decision. Okay, so assuming you have a definite size that you actually want, uh, you can add +1 or -1 and then make the purchase, and you'll be very sure that actually that purchase will not be uh, redundant because you have not chosen the appropriate size. Okay, so choosing, for example, let us use the example of the the blood pressure cuff. Okay, we know that the accuracy of the blood pressure relies a lot on the size of the cuff. That we definitely have what you call pediatric cuffs and then adult cuffs, but adult cuffs actually may not really apply for all adults. There are also size variation. Okay, so if you buy a particular size and then for most of the people who are actually closer to the mean, it will work. But if you add one smaller and then one larger, it's like the positive and then the negative end, you're going to be covering almost 68% of the population. You know that um, for the three types of adult cuffs that you have bought, at least 68% of the people who come to the facility will be able to take their blood pressure accurately, because you have the accurate or you have the appropriate size of the blood pressure cuffs. So that is the implication. Therefore, the distribution actually enables us to make predictions. And then the last one is the regular distribution. This one actually doesn't have tails, but the data is narrowed towards the mean. And this happens for rare cases. For example, if you want to know how many people have uh, all their 10 fingers, you most likely find that almost all people have 10 fingers and you not have extremes. So you find it that the curve will actually be narrowed. So you get what you call the regular distribution. Thank you very much for listening.